some examples where we estimate limits numerically. So we have two functions here. One is x divided by the square root of x plus 1 minus 1. And we will find that the limit as x approaches 0. Now your first thought might be, we'll just plug in 0 and see what happens. That's a good thought. You should do that. If I do that, I get 0 on top, no problem. And I get 0 plus 1, which is 1. Square root is also 1. Minus 1 is 0. So I have this 0 over 0, no dice. We've got to do something different. Now in this one I say x equals 1. Well that's, let's say it's 3 plus 3 minus 6 is also 0. 1 minus 1, 0. Darn. Okay. So in these cases we've got to solve this another way. Now we're going to estimate these numerically, and we're going to learn how to solve these actually analytically in a coming section. But first let's go ahead and do this. And I've got some printed out values on a table. Normally I'd work problems out standardly, but this is not worth the effort of doing that. Or at least not worth your time to watch me crank it out by hand. So, on the first one, we're going to have some values. So as we come from the left, we have these we come from the right, we have these increasingly, we come from the left, we come going right, shouldn't have second guessed myself. We have these increasingly small magnitude, they're technically larger, values, they're getting closer and closer to 0 here. So 01, 001, 0001, and your value of the function there is 1.99, 499, 1.99950, so a little bit larger, and 1.99995. Now, if you were a betting person, I imagine you could bet and see about what you think that limit's going to be. But let's keep going. So now let's get a little bit larger than 0, 0.0001. 0.001, 0.01. Now we're getting sort of further away here. And we have 2.00499, 2.00050, and 2.00005. So it's pretty straightforward to see that these are very, very close to 2. So in here we would say that that limit is 2. At least we would estimate that. Now we can prove that with techniques we're going to learn later. So that's kind of the basic idea. This is a really good example of why it's helpful to know how to use calculator. Personally, for this type of stuff, calculators might be useful on small scale things, exams. Personally, I would recommend learning some sort of programming language, even if it's a relatively simple one like Python, or even dealing in like MATLAB or Maple, because this is going to make your life a lot easier. So for instance, like this problem, I was able to run some values using Python programming and generate these outputs to check my numbers again. So what I did for this problem here is I ran 0.9, 0.99, 0.999, and 0.1. So I ran these 6 numbers. Now I could get even more fine-tuned if I wanted to. The nice part about doing this in the programming language is you can get really, really finely tuned with it. Much more than you can with a graphing calculator because of floating point sizes generally and things like that. So you're going to be able to estimate limits very, very well. So when I did that, I've got my numbers here. I end up with 9 4 6s in the 7. 9.060606. So obviously that's a repeating. And 9.06 or 006. So technically, yeah, 006. And so notice that's repeating too. So what I have is these 6s. I have a 0 before that 6 repeats. I have 2 zeros before that 6 repeats. I bet if I stacked another 9, I'd have 3 zeros before that 6 repeats, and so on and so on. On the other side, I have 8.994 00599 0.94 059 406. I gotta get a bigger screen. 8.454545. So what I'm seeing here is, as I approach from the right, I get really close to 9. As I approach from the left, I get really close to 9. So those are going to be my estimated limits. And again, we're going to solve this analytically. But gosh, you got to get that intuition. Graph this stuff. Plug in numbers. Do something to help you out before you start plugging and chugging. Because if you get... I mean, who wants to work these problems for a while just to not even have any clue if it's correct? So this is kind of the basic process, and do a few to get that intuition yourself.